Hello, in this video we're going to use R to generate uniformly distributed points on the surface of a sphere. And this stems from the last few videos that I've been doing. In this video here I call BV1, Background Video 1, we looked at the multivariate normal random variable and how to transform it into a multivariate uniform random variable. And that's actually part of the theory that is used in developing a Wishart distribution. And in part of that, I thought it was just so cool that you can take a multivariate normal random variable, transform it with this transformation, and then it ends up plotting points around a sphere. So I was going to use this technique and show you an R, and then show you that how cool it is. In 2D it plots points around a circle, and in 3D it plots them on a sphere. And then I looked up, well, what other ways to do this? Surely this, I didn't invent this. And it turns out that there's two other common ways. So this is one common way, and there's two more. And I couldn't really find the theory on why it all worked. So I just did it. I created a video that talks about the theory of why these three methods work. And that's in what I'm calling BV3. I'm also including BV2, which is on spherical coordinates, where one of the approaches is using spherical coordinates to generate these points on a sphere. So let's get started. So let's load scatterplot 3D. And is that the best package to plot three-dimensional objects? I don't know. It's just the first one I came across, and so that's what we did. So we're going to work in R2 space first, and we're going to create 200 vectors, two-dimensional vectors, 200 tuples, and that's what the K and the 2 stands for. Now we're going to put them in a matrix X, and so that X is dimension 200 by 2. And then we're going to use this transformation here. And the way to do that in R is we're going to take X times X and sum the rows and square root them, and then take that and divide it by each of the components in X, put that in Y, and then we plot it. And here are 200 points randomly put around a circle. Isn't that so cool? I'm going to highlight it and plot it a few times. Here's another version. Here's another version. We can add points to this. Let's say there's 500. And then of course they're a lot tighter around this circle. But that's one approach. And actually I read one article. Now they didn't talk about the theory of why these three methods work. They plotted it, and they also investigated which method or which approach is most efficient. And they determined that doing it this way with the multivariate normal distributions is actually by far the most efficient way to generate points around a sphere. Now here we do spherical coordinates. So here in this approach, what we do is we generate the random angles and then plot them back in spherical coordinates. And so when you do that, you get points around a sphere. And so the T1, it's theta 1, and it ranges from 0 to 2 pi, and then you put it back in X and Y, and then you plot it. And in here we can also generate more data. Let's do it for 1,000, and it ends up like this. And that's just, it has a radius 1, and these points are uniformly distributed around that circle. So here, now this one, it's like rejection method or rejection acceptance method. So what it basically does is it generates random numbers between -1 and 1, and then if the length of that vector, so it's a tuple, so if the length of that vector is more than 1, you get rid of it. If it's less than 1, you keep it, and then you transform that vector so so you normalize it so it extends it to the circle. And so since there's, we're creating numbers that, vectors that may not be accepted, we actually have to randomly generate more than 200 vectors to get to 200. And so what I do, like you could do this sequentially, generate a vector, see its length, if it's accepted, if it's less than one, accept it. If it's not, reject it, and then keep going until you get to 200. But on the theory, you know the area of a circle and the area of that square, so you can roughly determine the proportion of acceptance and rejections. And actually that's what this ceiling does. So the n times 4 divided by pi, that's, the 4 divided by pi is the proportion that we need in order to get approximately 200 random vectors. And then you have to take the ceiling, because you have to have a whole number when you're creating a matrix, because that determines how many rows and vectors. And so this one here, so it looks at the length of each vector, and then this is the transformation that we use, and then we plot it. And then I also plot out the dimensions of y, just to see how close we were at getting 200 vectors. So when we plot this, here's the points around the circle, and notice that the dimension is 196. So it's 196 rows by 2. So we were close to the 200 vectors. So let's do it again and see if we can get, just out of curiosity, run it again. This time we got 206 vectors, and this is just approximating based on theory. So let's do 500 vectors. Now you're going to have to create much more, than 500 randomly picked points to get to 500. So, and that's why this method is actually pretty inefficient. And here it is. And it actually shows that the higher dimensions you go, the volume of a sphere shrinks. And so it actually limits to 0, I think. I'd have to look that one up. And so the number of points that you're throwing out increase in higher and higher dimensions. So now let's look at 3 space, and the beauty of the matrix theory, this is the same 3 rows that I used upstairs in the, above in the program, except for I put k equals 3, and then I use scatter plot because there's 3 columns instead of 2, and we plot it, and these are points around a sphere. Okay, and that is fast and efficient. Let's do 500. See what it looks like. Boom, there it is, 500 points. Now, if we do this in spherical coordinates, we have to find the distribution of the theta 1 and theta 2, and that is in actually BV3, background video 3, if you want to understand the theory of why generating theta 1 and theta 2 with these 2 lines is the reason why. So let's just do it with 300 points. And so there we've generated random theta 1s and theta 2s, and then now we put them back in X, Y, and Z, and then we plot them, and we get this. So those are the random points around the sphere. Now let's look at the last case. Here we're generating random numbers from 0 to 1. We're doing it 3 times. So we're at 200. We want 200 samples. We need 3 of that, so we need 600 randomly generated points. Then we and that's what these first 2 lines do. And then the 6 divided by pi is actually proportion of data that I think we'll need to approximately get to 200 random variables. And then we check it to see if it is, the length is less than or equal to 1. Then we create the transformation and we plot it. And then I I put out the dimensions of our vector because I want to see how close we came to 200, and we generated 229. Let's do it again. And here we need 179, or we attained 179. There's 195, and these are all points that are randomly just around the sphere. So let's do 800. And here it is. Those are randomly distributed, uniformly distributed around the sphere. And this time, the theory got us 799. So again, I'm just approximating how many we're going to need based on theory. If you needed exactly 800, you'd have to do it one at a time. See if it meets the conditions of the length of it less than 1 or not, and then keep going until you get to 800. So, well, anyway, that's all I have for today. I hope you enjoyed that. I sure did. And as usual, I'll put this code in the comments so you can copy and paste it and play with it. This to me is just so fascinating and cool how it all works. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.